All right, hello everyone. Welcome to the second part of the video for section 4.7. We're continuing on with our applied optimization problems. I will again encourage you to, if you have not already done so, start working on the problems in this homework problem or this homework set. They are some of them are quite difficult and quite lengthy, so this is not something you want to wait until 11 p.m. the night that it's due to begin, because I promise you, you will not get it done. So hopefully you are already working on these problems, but if you're not, please start right after you finish watching this video. Okay, in the last video we talked about kind of a general problem solving strategy for solving optimization problems. This is from your book. And as I said before, this is not the type of problem where I can just tell you how to do it every time and you can follow the same process. It's not something like the power rule. Each problem requires a unique approach. So I'm trying to show you some different examples of problems you might encounter, but this will not work for all of them. So this problem-solving strategy here kind of helps to generalize it. And some of the big takeaways: introduce variables to represent the things you don't know, write formulas, try to figure out what it is you're maximizing or minimizing, consider the domain of the variable you're looking for and whether or not, or what kind of the bounds are for that. And then remember, this course is all about derivatives, so at some point you should take a derivative and set it equal to 0. That's one of those things that once you leave this class, that's hopefully one of the things that's tattooed on your brain when you go on from here. All right, so let's look at an example of minimization. Both of the other ones we looked at were maximization problems, so let's do a minimization one. And so we've got a cylindrical can that's going to be made to hold 1 liter of oil. And we have to find the dimensions of such a cylinder in centimeters that will minimize the cost of the metal to manufacture the can. Okay, so even though this is a pretty short wording for the problem, there's a lot going on here. So first of all, we see that the can we're looking for needs to hold 1 liter of oil. We have to find the dimensions in centimeters. We're trying to minimize the cost of the metal to manufacture the can. So one thing I see right away is that we're given information about the can in liters, but we have to find dimensions in centimeters, which means we have a crisscross there in the units that we're using. So to fix that, we need to put everything in terms of the same units. Since the answers we're looking for, the dimensions of the can, will be in centimeters, we'll want to take that 1 liter and convert it to centimeters. And do y'all know a conversion between liters and centimeters? Right, I could hear you say it all the way from here. 1 liter is the same as 1,000 cubic centimeters. And if we're talking about the amount of oil the can can hold, and that's 1,000 cubic centimeters, that represents what about the can or the cylinder we're looking at? Right, that's talking about the volume. Okay. All right, next thing, we're supposed to minimize the cost of the metal to manufacture the can. Now, think about what are we really looking to find here. We're trying to minimize the cost of the metal. Well, the metal used to make the can doesn't really have to do with the volume, right? It doesn't have anything to do with what's the space inside the can. In fact, right, if you're making the can, if you fill it up with metal, you can't put anything in the can, right? So it doesn't talk about that. So it really talks about the material on the outside of the can, right? So kind of like the top here, the piece that is wrapped around the outside here, and then this piece on the bottom. So what are we referring to there? Well, that would be what we call the surface area. Okay, because the amount of metal we use is really going to correspond to the area around the outside of the can. And in order to talk about the surface area of the can, I'm going to need to add some dimensions here on the can. So I'm going to, on the top here, call this length here R, is the radius of the circle there on top, and that was supposed to be an R. I'm going to try to draw it better here. Okay. And then the distance between the top and the bottom of the can, I'm going to label that as H. That's going to be the height. And you may remember that to find the surface area of a shape, you have to find the area of all the faces we can see. So notice, for example, two of the faces we can see, I just kind of highlighted this, are the two circles on the top and the bottom. So we know that the area of a circle is given by pi r squared, but there are two of them. So we'll do 2 times pi r squared. And then if you remember, if we kind of unwrap the lateral surface area, the area around the outside of the can, what you get is a rectangle where the height is h, so that's still this. And the distance along the top here, we'll notice that corresponds to the distance around the outside of the circle. And what do we call that distance around the outside of the circle? That's right, that's the circumference. And the formula for that, you may remember, is 2 pi r. So the area of this rectangle here then is going to be 2 pi r times h. So just 2 pi r times h. Okay, so now we have our formula for our surface area. And this is the part, whoops. This is the part that we need to minimize. Now notice one of the problems with this is that we have two different variables inside the formula. Now, and that's a problem because if we want to take the derivative, we'd maybe have to use something like implicit differentiation. However, part of the problem here then is we can't really do a related rates type thing because we also don't have anything about rates of change of these variables. So I want to somehow write this formula here in terms of a single variable. And to do that, we can actually use this information about the volume we have up here. So notice we have that the volume of the can is 1,000 centimeters cubed. And if you also recall the formula for the volume of a cylinder, well, it's the area of a base, which is pi r squared times the height. And here we can actually solve for h. So dividing by pi r squared. And if we do that, notice what we get is that h equals 1,000 over pi r squared. Okay, and now we can take that and plug it in for h up here. So our formula is about to get a whole heck of a lot more fun. Okay, so if we do that, so we have 1,000 over pi r squared, and erase this stuff. Our formula will now become the surface area is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And here you notice we can cancel some stuff out. We have a pi here and a pi here, and cancel the r here with one of the r's down here. And so when we do that, then we end up with our surface area formula being 2 times pi r squared plus 2,000 over r. Okay. All right. So now we're going to take a derivative here to try to find the minimum. Before we do that, though, let's think about some bounds on r. And unfortunately, in this problem, we don't have a whole lot to go off of. We can for sure say that the value of r has to be greater than 0. But the other piece of information we're given here is that the volume has to be 1,000 cubic centimeters, and that in no ways tells us about what's the max value r can be, because we don't really have information about that. So right now all we know is that r has to be bigger than 0, which is probably not surprising because if the radius was 0, the can would basically not exist. Okay, so we're going to have to take the derivative of this formula, and I'm going to go ahead and clear things out here so we can start with a nice clean screen. So our surface area formula now is 2 pi r squared plus 2,000 over r. And I'm not going to go through all the steps of this. We'll use the power rule. The r here, you'll want to bring up and make r to the -1, so that when you take the derivative, we should end up with 4 pi r minus 2,000 over r squared. Okay, and you can double check me on that. We can set this equal to 0. So we'll have 4 pi r equals, or excuse me, minus 2,000 over r squared. To solve this, actually move this minus 2,000 over r squared to the other side. Okay, so I'll pause to make sure everyone's got that. So I'll add it to both sides. And we do this, and again, I apologize, I have to clear out the screen. We'll end up with 2,000 over r squared equals 4 pi r. The 4 pi r, I can make 4 pi r over 1. And then I can do some cross, I thought I put it over 1. There we go. I can do some cross multiplying here. And so when I do that, I'll end up with 2,000 equals 4 pi r cubed. Divide by 4 pi. And so we'll end up with r cubed equals 2,000 over 4 pi, and then solve by taking the cubed root on each side. So we end up with then that r equals the cubed root of 2,000 over 4 pi. Okay. And I realized, oh yeah, and we can actually, sorry, I should have done this before, reduce the 4 and the 2,000 there, so we can make this the cubed root of 500 over 4 pi. Make that our final answer. All right. Now, what was the other thing I wanted to say about this? So you can plug that in the calculator and get a decimal answer there. And then we can use that to find h. Before we do that, though, we definitely want to check and make sure this is a minimum. So what I would do in this case, since we can't really do what we did before we plug in the endpoints because we don't really have an endpoint besides 0 here, is set up a number line, put the cubed root of 500 over pi here, which that is about the same as 5.419. Okay, choose values on each side, plug them in the derivative, see if you get positive or negative numbers. As we know, it's 0 here. And I've already done that, and I know that this one is negative, this one is positive, so it looks like we have a shape that does something like this. So we do know that that's a minimum. So we do know this will be our value for r that minimizes things. And then to find h, we can go ahead and plug in this value into that formula we had for h, which was 1,000 over pi times r squared. So we do cubed root of 500 over pi squared. And if we do that, what we end up with is 10.839, which of course we should put that these are both centimeters. Okay, so those will be the dimensions that minimize the amount of material needed to use for the can. Cool. You guys having fun with these yet? Yeah, I figured you were. All right, let's do another example. So this one, for those of you who have taken Math 141 at Pierce, this problem might look kind of familiar. And if you'll remember, when you did it in 141, we had to use graphs to figure this out. But now we have this added tool of calculus we can use. Okay, so here's the situation. We have a rectangle that's inscribed with its base on the x-axis and its upper corners on the parabola y equals 12 minus x squared. We want to know what the dimensions of such a rectangle are with the greatest possible area. And if we're trying to find the greatest possible area, what does that mean here? Are we trying to maximize or minimize something? Right, we're trying to maximize. Okay, so first things first, just like we've done on the other problems, let's draw a picture. So here's my coordinate axes. I've got this parabola here that is y equals 12 minus x squared. You can double check me that that'll look something like this, where it intersects here on the vertical axis at a value of 12. Okay. And then we're trying to create a rectangle whose corners are on the parabola, upper corners, and it's based on the x-axis. So we're trying to create a rectangle that is going to look something like this here. Okay. And let's go ahead and label some stuff on here. So notice, first of all, that for the lengths along the horizontal axis, this one and this one, first of all, they're going to be the same because we see there's some symmetry here. And notice that the length along there is going to go over to some value of x, right there. And so that tells us, first of all, that this length here on each side will be whatever that value for x is. Now we're trying to figure out the one that's going to maximize the area, so we don't really know what it is. So right now we'll call it x. And then we want to figure out, based on that, what is the height of this rectangle? So this part here. Well, notice, once we have a value for x, right, the height up to here would come from plugging x into the function, that parabola there, which would mean taking this value for x and plugging it in here. And if we do that, then we get this height turns out to be just whatever we get as our output, which, since we're using a general value for x, in this case is going to be 12 minus x squared. And if that doesn't make a lot of sense, think about how if x was equal to 1, we'd plug in 1 here. So we'd have y equals 12 minus 1 squared, which is 11. And that would be the height of the rectangle right there, because you have to go up that much to get up to the parabola. Okay? So what this does now is we have some dimensions of the rectangle, right? And we're trying to maximize the area. We know that an area of a triangle, or sorry, a rectangle is given by length times width. And here our length is going to be that entire side along the bottom. This one here, which is going to have a length of x plus x, which is just 2x, times the width now, which is that height there, which is going to be the 12 minus x squared. We can multiply this out and give us 24x minus 2x cubed for our area formula. I'm just quickly referencing my notes to make sure I've not made any mistakes yet. Okay, so far so good. Let's also put some bounds on the value for x. So what is the smallest value x could be? Well, right, it's if there was no distance right here, it would be a 0, right? And then what is the largest? Well, it looks like from the picture, the furthest out we could go along to this side and still have a rectangle that touches the parabola would be to that point where the parabola intersects the horizontal axis. And how could we find that point? Right, we could take the formula for the parabola, set it equal to 0, and solve for x. And if we do that, you would find that we'd get that that number there is square root of 12, or 2 root 3, as the max value that x could have. Okay? All right, so now that we have that, so I'm going to clear, am I going to clear? Yeah, I'm going to clear this out. So again, we have our area function is 24x minus 2x cubed, and then we have again that x is between 0 and square root of 12. Take our derivative. So a prime of x equals, using the power rule, 24 minus 6x squared. Set this equal to 0. Solve for x. And you'll find that when we do, we end up with x equals plus or minus 2. However, notice that the negative here, that is not in our range for x over here, so we can count that one out right away. So we know we have to use the plus 2. And then we'll take that along with our endpoints, plug them into our area function. So we'll do area of 0, plug that into the area function here. Not that one, sorry, this one. We get an area of 0 units squared, which is not what we're looking for. If we do a of 2, what we see then is that we get an area of 32 square units, and I should put that on here too. And then if we do a of root 12, you can double check that if we plug that in, we also get a 0 units squared. So it looks like the number that maximizes the area is this one here when x equals 2. Now, are we done with this problem? Hopefully you're saying no, right? Because notice what the question asks for are the dimensions. So we need to figure out what the length and width are of the rectangle now that we know that the value for x is 2. So to go back to our picture, okay, I'm going to draw it like this. So we just found out that the length here is 2, and this one will also be 2 then. And then we saw, based on our analysis, that the width here will be given by y equals 12 minus the value for x, which is 2 squared. So we'll have 12 minus 4, which gives us 8. These two together give us 4. So that we see that the dimensions of the rectangle with the greatest possible area then are going to be 4 units by 8 units. So it'll actually be taller than it is wide. So not, the picture that I have here is not representative. So we have that. Okay? All right, thanks for watching.